So let's continue with circular motion here. We've got horizontal circles that we're going to look at now. So much like a car driving around the road. So imagine that you're in the car and you're turning a corner. What direction are you accelerating in? Well, okay. You were going forwards. Now you're going that way. Something has to push you to make that turn. We've already established that for an object going in circular motion, there has to be some sort of inward force. And so for a car driving around a corner, what you have to have is some force inward so that you'll actually make the turn. In the case of a car on the road, that inwards force is the friction between the tires and the road. So friction's actually pushing you in. You want to continue going straight. It's the friction between your tires and the road that are making you turn around there. And so if force is in that direction, acceleration has to be as well. So in this case, this force is, I'll put it on this side, friction. And your acceleration's headed in. So there is a name for this. The force here is called a centripetal force. It's Latin. Means towards, which is the pedal part, and the center, which is obviously the center part. There's some notation that we're going to use here. So we're going to use A sub C, which is the centripetal acceleration, and then F sub C, meaning the centripetal force, not centrifugal. That doesn't exist. So often you'll see it like this. For the bulk of this, I'm not going to necessarily use these subscripts. I may not. I could forget. I could do it. But generally, that's what those mean, A sub C and F sub C. But we could also just consider the F net and the A, and then you could recognize that we're in a unit on circular motion. And so then that's the acceleration is inwards, and the net force that we're talking about is inwards as well. So we're going to do a couple examples of these calculations and let you to trying some of these things. So we've got a plane. I don't know if you've seen these before. There's a plane attached to a wire, and that wire is attached to the ceiling. On the front of the plane, there is a propeller. And then this thing starts to fly in circles. So it's coming up out of the page at us, looping back around, and heading in. If we ignore air resistance, what is going on here? So we're going to free body diagram this thing. We've got a force downwards, and that's force of gravity. We've got a force here, and that is the tension on the string. Whenever we've got a string involved, we know there's a tension there. But what else is going on? This plane is flying in a circle, and it's not raising or dropping. So we know a few things have to be true. In a circle means that there has to be some sort of inward acceleration or inward force to the center of the circle. And because this thing is not raising or falling, we know that something has to be balancing out gravity. Well, we can break the tension up into components here. We can see the tension's going off at an angle. So there's actually a component of tension. I'll call it Tx. And it's this component of tension that's actually dragging the plane in, keeping it in a circle. And then we've got Ty here. And that's the component of tension that's preventing the plane from falling to the ground. And so we've got a few things that we know are true here. We know that Ty equals Fg. And if we go back and we look at what we had for net force from before, I was going to walk us through how this question would look. We've got F net equals ma. Now we're in circular motion. I could put F net sub c and a sub c. I'll put that there. And there is only one force that is acting inwards, and that's that little guy there, Tx. So we're going to have Tx equals m a sub c. But if you remember back to the first lesson, because this object's in circular motion, we have an expression. I'll zoom this out a little bit here. We have, excuse me, an expression for the acceleration. We know that for an object in circular motion, a sub c is equal to v squared over r. So we can plug that in here, and so we're going to get the tension in the x direction is equal to m v squared over r. And we've got one more piece that we can deal with here. We've got the angle that the plane is flying at. So we've got expressions for ty and for tx. For ty, because that's there, this is the adjacent side of that angle. So this guy here is going to be t cos theta, which means this guy is going to be t sine theta. So we're going to have t cos theta equals fg, and we're going to have t sine theta equals m v squared over r. We've used our f-net equation, which doesn't change. We've used the acceleration in uniform circular motion. So the expression for that is v squared over r. We've plugged everything into our equations, and now we've got two of them. We've got t cos theta equals fg, and we've got t sine theta equals mv squared over r. And now we could theoretically go through and solve the rest of this equation. We don't know the mass of the plane. We don't know how fast it's going. We don't know how big the circle is. Like, there's so much information we don't have. But this is how we would set up the formulas in order to solve it from there. So flip the page. We're going to take it a little bit further here. So I'm going to redraw what I had on the previous page. We've got tension. We've got Fg. I'm going to break tension up into its components. We have Tx equals T sine theta. We have Ty, and that's going to be equal to T cos theta. We know the force is up equal my force is down. And so that means that Ty equals Fg. So T cos theta equals the force of gravity. And we've got uniform circular motion. It would help if I could spell. Uniform circular motion, which gives us F net C equals MAC. And then if I go all the way to the end of what I had before, I'll just skip to that point. I get T sine theta equals M V squared over R. So if we take a look at what we've got here, actually there's one more piece I could do here. We know Fg equals Mg, so T cos theta equals Mg. And now we don't have a lot of information, but we can still go through and I'll show you what it looks like to actually solve this thing. So one of the techniques that we've used before, we're going to use it again, is I'm going to label these equations. This guy here is going to be my equation 1, this guy here is going to be my equation 2, and I'm going to take equation 1 and I'm going to divide it by equation 2. And then what that's going to give me is T sine theta equals mv squared over r divided by T cos theta equals mg. And now we're going to see what happens here. My t's are going to cancel. My masses are going to cancel. And we've seen, lots of you guys in Math 12 have seen that sine theta divided by cos theta is tan theta. So we get tan theta equals v squared divided by rg, which is a neat little expression. We can find the angle that a plane will fly at. It doesn't matter what the mass is. It only depends on the strength of gravity on whatever planet you're on, so Earth, the radius of the circle, and how fast it's going. So we've got all the information wrapped up in this little equation here, independent of the mass of the plane, which is pretty cool. Do 2 more examples. The picture below shows a frictionless tabletop. So we're looking down at a tabletop, much like my document camera is right now. We've got a mass attached to a string, and this mass is moving in a circle at 2.5 meters per second. We know the string is 2 meters long, and we know the mass of the object is 4.15 kilograms. So now we're actually going to go through and we're going to solve some stuff. Because this is a string, well, first we're going to free body diagram this thing. Because this is a string, this is tension. And this is also the inward, like this object's in circular motion. That tension force is the inward force that's driving this guy in here. Gravity would be down into the table, and Fn would be straight up, so we can't draw them. We're not going to. It's okay. So if we get F net C equals MAC, the net force inwards is that tension. So that's going to be T. We've got M. And now if we recall, AC is equal to V squared over R. The acceleration inwards is equal to the speed of the object squared divided by the radius of the circle it's traveling around. So we're going to get M V squared over R. So now we can plug some stuff in here. Tension equals, we know the mass is 4.15 kilograms. The velocity of the object, we are told, is 2.5 meters per second. We're going to square that. And we know the radius of the circle. How do we know that? Well, it's a 2.5 meter long string. So the circle has to be 2 meters, or sorry, it's a 2 meter long string. So the radius of the circle has to be 2 meters. That's ignoring this little part of the distance right here. So if we solve that, we can see that the tension in the string is 12.97 newtons. That's how we go about approaching something like that. Let's do one more example, and then you guys can practice using forces in uniform circular motion to solve some of these problems. So this is kind of an awkward looking picture. Basically what we've got here is the car is, like this circle is kind of, we're at an angle, so this is like the horizon, it's going up and around the circle that way. So this is the back of the car that we're seeing. The car is going forward. The car is making its way around this bend. So if we free body diagram this thing, gravity we're going to have straight down. Technically it would be angled because the road's slightly angled, but whatever. For the sake of our drawing, FG is straight down. And FN is going to be straight up. Assuming the road, we're told that this is a flat corner, even though the drawing is terrible and doesn't look like it. So we know something is true about Fn and Fg. If this is a flat corner, these two have to be equal. There's no inclines going on here. We can look at that later. It's going to be a good question. And we've already established that the force that's causing a car to go around in a circle is the friction between the road surface and the tires. So I can just label that the force of friction in. So we've got a few things here. We've got my forces up equal my forces down, which means Fn equals Fg. And we also know that because we're in uniform circular motion here. Uniform circ mot is how I'm going to start abbreviating this. So we've got Fnet C equals MAC, which means we've got force of friction is my only force inwards, equals the mass of the car times, remember here, AC equals V squared over R. So M is going to equal V squared over R. There's some interesting results that we can get just by looking at this. We're going to recall some stuff here. Force of friction equals mu Fn. So we're going to insert that here. So we're going to get mu Fn equals mv squared over r. We've already established that Fn equals Fg, so I'm going to shove that in there. So I'm going to get mu Fg equals mv squared over r. Well, we know that Fg on Earth equals mg, so I'm going to get mu mg equals mv squared over r. Our m's can cancel. We divide by g, and we're going to get that the coefficient of friction between the tires and the road surface is equal to v squared over rg, which is an interesting result. We've already seen this result. We saw it for the angle of a plane flying in a circle. Now we see it for the coefficient of friction for a car going around a circular corner. So the last we had was true for the plane on the string. This one is true for the car. What's interesting is it doesn't actually matter what the mass of your car is. But we've got to be aware of what kind of, or what this coefficient of friction actually means. This is not the maximum static coefficient of friction. This is just the current coefficient of friction. This could theoretically increase or decrease depending on the max speed of the corner and all that kind of stuff. But effectively what we've got here, though, is the coefficient of friction dependent on the speed of the vehicle, the radius of the corner, and the gravity of the planet that you're on, which is pretty cool. That's the last example I'm going to do. I'm just kind of trying to show you guys how to use the concepts that we've got to apply to these questions, or how they apply to these questions, rather. So I'm going to give you some problems to try. I want you to take a look at 1 to 3. I want you to take a look at number 5. And I want you to take a look at number 9. As always, if you've got comments, questions, concerns, fire me an email or come to my office hours.